All right, hello, welcome to this week's Math 2414 weekly review. All right, so this week we're going to be covering only two sections, section 10.3, which is going to be over polar coordinates, and section 10.4, which is going to be areas and arc lengths with polar coordinates. All right, so let's go ahead and get started with our section 10.3. All right, so normally in our other coordinate systems, what we do is we normally think of things in x and y. We have an x-axis and a y-axis. And our points are usually in x and y. Now, last week we talked about parametrics. And parametrics is whenever we have x and y, but those are both defined by a different variable. Well, polars are kind of similar. So let's actually go ahead and discuss this. So polar coordinates. So when we see polar coordinates, they are represented by the ordered pair r theta. And in this case, r is a radius and theta is an angle. But what are r and theta really referring to? Well, let's go ahead and talk a little bit more about our polar coordinate system. So when we have a polar coordinate system, we start off, we have a singular point that we call the pole. And that can, or you can also refer to that as the origin. So let's go ahead. So yeah, we have our little pole right there in red. And then we create a ray from that point called our polar axis. And it is essentially a ray starting from the pole. So we have our pole, and then we just go ahead and then we draw a line out, and then this is going to be our polar axis. Now, the polar coordinate system is a little bit different from some of the other ones we've talked about because unlike Cartesian, where we have an x-axis and a y-axis, we only have the singular polar axis in our polar coordinate system. So let's go ahead and talk about r and theta again. So whenever we're referring to r, or our radius, in our polar coordinate system, we are essentially talking about how far out from our pole are we going. So for example, if we have an r equals 3, we go 1, 2, 3 units out. If our r is 2, we'd only go 2, and so on and so forth. Whereas our angle is referring to our direction. So just like whenever we cover, when we first learned our unit circle and everything, we measure our angle going counterclockwise from the origin. So now let's go ahead and get in to how we can actually go graph these. So kind of just drawing like another clearer picture. So we go ahead and we start with our polar axis. So yeah, once again, just drawing a more visual picture. We have our origin right there. And then we can go ahead and say that we are going, and let's say this is our point, our theta right here. Essentially what this means is that we have gone, is that we went over and we measured going counterclockwise from our polar axis our value of theta. And once again, this right here represents that we have gone our units. And another thing that is important to come up. So let's say that we have a negative theta. If we have a negative theta, and once again, it's just like when we kind of talk about unit circle and things like that, we just kind of measure going clockwise. And then another thing that can happen is if we have a negative r. So if r is negative, essentially what we do is you go r units over. So for example, like let's say we're going r theta. You go r units over, but then you add pi to the angle, so therefore you're in the exact opposite 180-degree line. So then therefore, this would be like a representation of negative r theta. So yeah, the amount of units you go is the same. Your reference angle is still the same. You just move it 180 degrees. So now let's go ahead and try plotting some points. So our first one that we can plot is going to be 2 and 5 pi over 6. Next one we can try is going to be -2, 3 pi over 2. And then the last one we're going to do is 3 and -pi over 3. Alright, so for all three of these, we need to go ahead and start off with our polar axis. All right, so let's go ahead and start with our 2 5 pi over 6. So this one's simple enough. Everything's positive. So what we just do is we go ahead and we can say that we're going to go 1, 2 units over, and then we travel 5 pi over 6 radians. But we have to make sure we keep that distance the same. So if we go ahead, this is about 5 pi over 6. Well, actually, a little shallower than that, but there we go. So what we want to do is we take this and we just travel in a circular path until we hit that 5 pi over 6. So, yep, that's about where we can stop. So then therefore, that point right here is going to be our 2 5 pi over 6. Yeah, the angle got a little off, but it's fine. So now let's try doing -2 and 3 pi over 2. So typically what I would do with these first is go ahead and draw and start, just keep everything positive at first. If you like, just pretend we're going to take the absolute value of our radius. So we're going to go 1, 2. And then they want us to go to 3 pi over 2, which we know is going to be straight down. So we're going to go up. Now, this point right here is going to get us to 2 and 3 pi over 2. But remember, we had a -2, so what we do is we add pi to this. To where we go back up and around one more time. So then therefore, this point right here is going to be our -2, 3 pi over 2. And then lastly, we have our 3 -pi over 3. So this one, once again, this one's pretty simple. We can just go 1, 2, 3 units over. And then we just can go down, go to -pi over 3. So we're just going to go ahead and travel. Is just travel on a circular path, except you're going to go clockwise this time. So where this point right here is going to be our 3 -pi over 3. So yeah, those graphing our points, that's going to be pretty simple. So another important thing is whenever we're in polar, these points can actually have multiple representations. So in Cartesian, so let's think about this. So in a Cartesian system, if they say our point is going to be 3, 4, there's only one place on that graph where 3, 4 lies. But whenever we have polar graphs like this, whenever we think about polar, because we're traveling and we're keeping that, if we keep that radius the same and we keep going around the circle, we're eventually going to hit back to where we started. So therefore, whenever we're talking about polar, it's important to remember that we have multiple representations. So if we have the point r theta, in order for you, you can rewrite this as, you can find essentially equivalent points, because essentially you'll end up in the same point in space. So the other ways that we can write this could be r and then theta plus 2 pi n, where n is an integer. And this makes sense because anytime we travel to pi, that just means you've made a complete rotation and you're back to where you started. The other representation that you can use is negative r and then theta plus 2n plus 1 pi. And once again, n is an integer. So this once again makes sense because we learned this 2n plus 1 is going to make sure that we're multiplying times like odd multiples of pi. So pi, 3 pi, 5 pi, all of those. And we know that that takes you in a complete opposite direction of what your initial angle was. But that negative r is essentially saying, hey, add pi again, then that's going to take you right back to where you started. So like, for example, we have that negative 2, 3 pi over 2. But we could rewrite that as saying, for example, we can just travel 2 pi one more time around that and say that we could have negative 2, 7 pi over 2. Since that's essentially just taking one more rotation from this point. Or we can also say that this could be 2, 5 pi over 2. Because in that case, we're not having to switch sides again. So if we have our 2, 5 pi over 2, then we can just go our 2 units out and then just go 1, 2, 3, 4, 5 pi over 2. And we end up in the exact same spot. All right, so just like we could do with parametric, we can also convert polar and Cartesian with each other. So first of all, let's think of this graphically. So typically what I've been doing is whenever I've been showing you your polar axis, hypothetically, it can point any way you want. You just have to keep track of your angles. But there's a reason why we tend to have it be a straight line going out to the right. It is because this can help us correspond with Cartesian, and also just to kind of standardize it. So if we have our polar axis like this, we can essentially lay it on top of our xy plane in Cartesian. And then if we have a polar coordinate, our theta on our polar axis, this can be converted to x and y pretty easily. Because what we can do is we can essentially draw this as a right triangle. So we go, we can draw it as a right triangle from the origin. And then we can use our Pythagorean identities and just our other trig identities to go ahead and solve for x and y. So whenever we do this, we can discover that x is equal to r times cosine of theta, and y is equal to r times sine of theta. So that's a pretty simple way to go get from Cartesian from polar. But if we want to go the other way, there's also some other, we also have some other identities that work. So if we have our Pythagorean theorem where we have our x and our y, then we can get our r squared. So we can just say x squared plus y squared is r squared. And then we also have our trig identity that says that tangent of theta is equal to opposite over adjacent, or in this case, y over x. So now that we have these formulas, let's try to go ahead and convert these some points. So let's go from 4 and then 4 pi over 3 to Cartesian. All right, so we have our r and we have our theta, but now we need to find our x and y. So what we can just do is we can plug this straight in. X is equal to r cosine of theta, and y is equal to r cosine of theta to get us x is equal to 4 cosine of 4 pi over 3, and y is equal to 4 sine of 4 pi over 3. All right, so 4 pi over 3, that is going to be in our third quadrant, and our reference angle is going to be pi over 3. So if we do cosine of pi over 3, we are going to be getting 1/2, and since we're in the third, it's going to be negative, so we can get 4 times negative 1/2. And then sine of pi over 3 is going to be square root of 3 over 2, but since we're in the third quadrant, it's negative. So therefore, in Cartesian, 4 pi over 3 is actually equal to negative 2 square root of 3. We can also go ahead and convert the other way. So in this example, what we want to do is let's convert 3 and then 3 square root of 3 to polar. And usually in this, they usually try to give you some sort of stipulation. So in this case, we're going to say r has to be positive, and we're limiting theta in between 0 and 2 pi. All right, so let's go ahead and think about some of our identities that we can use. So we have our x and we have our y, and then we have our x and we have our y. So we still need to find our r and our theta. Well, we know we have an easy expression for r squared because for r that involves x and y, because we have x squared plus y squared is equal to r squared. So what you can do is you can just go ahead and plug in our points. So we have 3 squared plus 3 square roots of 3 squared is equal to 9 plus 9 times 3. So then that's going to be 9 plus 27, which is 36. So therefore we get r squared is 36, therefore r is 6. And then now we need to go ahead and find our angle. So we also have a pretty simple formula for our angle, which is going to be that tangent of theta is equal to y over x. So we can just go ahead and plug that in. Tangent of theta is equal to 3 square roots of 3 over 3. We can go ahead and cancel that out to get a square root of 3. So then theta is the arctangent of square root of 3. And if we think about our trig chart, so if we think about our trig charts, we know that the tangent of pi over 3 is square root of 3. And since we know that we have a positive y over x, we have to be in the first and third. And then if we look back at our two coordinate, and then we can see that our x and y are both positive. So therefore, that puts us in the first quadrant. So pi over 3 would work. So therefore, our final point would be 6 and then pi over 3. All right, so now let's go ahead and talk about polar curves and polar functions. All right, so whenever we have, we're in Cartesian, we tend to write functions as being y equals f of x or x equals g of y. Well, whenever we're in polar, we write our functions as functions of theta. So we can say that r is equal to f of theta. And it's also important to note, I'm probably not going to do any examples on this one today, but you can convert polar and Cartesian equations using the formulas given for coordinate conversion. And then whenever we are talking about polar curves and polar equations, we also need to learn how to graph these. So one way that we can go ahead and graph is to go ahead and just plot points. That's usually the easiest way to go ahead and start off with. There are some tips to make it easier that we'll go over in a little bit. So we're going to just do an do a relatively simple example. So we're going to do, we want to go ahead and graph r is equal to 3 sine of theta. So what I would typically do is I'd go ahead and build a table of your theta and your r. So let's go ahead and just put in a few points. So let's go and do 0, pi over 6, pi over 4, pi over 3, pi over 2, 3 pi over 4, 5 pi over 6, pi, and then let's just go ahead and start off with that for right now. You can always go ahead and plot more. So then we know that sine of 0 is going to be 0, so therefore our radius is going to be 0. At pi over 6, sine of pi over 6 is 1/2, so therefore we're going to get 3/2. Pi over 4, we'd get 3 times square root of 2 over 2. At pi over 3, we would get 3 square root of 3 over 2. And at pi over 2, sine of pi over 2 is 1, so therefore we get 3. 3 pi over 4, we'd go back and get 3 square root of 2 over 2. 5 pi over 6, we get 3 halves, and then at pi we get 0. All right, so let's go ahead and plot this and see what we have. So let's go ahead, we're going to go ahead and draw our graph. So then let's go ahead and start plotting points. We have 0, 0. Let's see, and it also looks like, oh yeah, I went ahead and just plugged this into a calculator to approximate. We're going to approximate 3 square root of 2 over 2 to be 2.1. And we're going to approximate 3 square root of 3 over 2 to be 2.7. So then we can go, let's say let's go ahead and just draw some units just so we can see. We're going to do 1, 2, 3. That looks good. All right, so we're going to go ahead and plot pi over 6 and 3 pi over 2. So, 3 over 2. So 3 up a little bit. I would say that, oh, let me just go switch colors. I'd say that's a good spot. And then let's go ahead. Our next one, we have our radius of 2.1 and that pi over 4. So we're going to go up a little bit. I'd say about right here. Then we have pi over 3 and 2.7. So we're going to go a little bit below 3. Go up a bit higher. And then we finally go straight up at pi over 2, and then we get a radius of 3. And then, let's see, our next one we said was about radius of about 2.1. And then we go over all the way into our second quadrant now. To get us, for our radius is 2.1, 3 pi over 4, and then we have our radius of 3 halves, all the way at 5 pi over 6. And then we have pi, we go back down to 0. All right, so now let's go ahead and try to go ahead and plug these in. Let's go ahead and connect what we have and see. Since it does look like we have a pretty clear shape now. So we can kind of go ahead and connect these. This is pretty ugly, but it's okay. So this graph is actually going to be a circle with a diameter of 3 and then going straight up. And this is going to be a form that'd be good for you to recognize. And then another form, so we have the form R is equal to some A sine of theta. And then if A is positive, you'll get something looking like this, going straight up. And then if we have A is negative, you'll get something like this. Another good form, and then the other main form for circles that we see is R is equal to B cosine of theta. And then if we see that, if we have a positive B, it will look something like this. And then if we have a negative B, we get something like this. So that just be a good one for you to go ahead and memorize. So now that we've, however, the thing is plotting a bunch of points can be kind of a pain sometimes. So let's go ahead, because if we have to go, and this one was easy enough because you're able to stop at pi. But there are some where you have to go all the way to 2 pi, and we can see how that can be kind of a pain. So let's go over some quick tips. Some quick little tips and tricks. So one thing that you can do if you just absolutely don't know where to go, you can try to convert to Cartesian. But that is if you absolutely are just completely stuck. And like when I mean convert to Cartesian, I mean using like the x is equal to r cosine of theta, y is r sine of theta. Another thing that, and there is another method we can use for Cartesian, using our Cartesian as well. So you can use a Cartesian graph, but what we're not doing is we're not trying to complete convertly. So for example, let's say that we have like r is equal to 3 sine of theta. That means you're going to look at the graph of y is equal to 3 sine of x. Because what this can do is you can go ahead, because then you can say that the y value is equal to your radius. So that helps you find some good key points to be like, okay, this will be an easy number to work with. And it also lets you know, and you can also see when your radius is positive or negative, or whenever it is, and you can also look and see when it's increasing and decreasing. So that's another good tip for you to use. And then another tip that we can use is actually symmetry. So if you see these patterns, then you can go ahead and apply them. So essentially, if f of negative theta is equal to f of theta, then your graph is going to be symmetric about the polar axis. If f of theta plus pi is equal to f of theta, you're going to be symmetric about the pole. And lastly, if f of pi minus theta is equal to f of theta, then you will be symmetric about theta is equal to pi over 2. So now that we have those, let's go ahead and try another example of graphing, but now that we have this little like idea to look at. Now that we have these little tips in mind. In this example, we want to graph r is equal to 1 minus cosine of theta. So one thing we can do is let's go ahead and look at our graph of y equals 1 minus cosine of x. And it's going to look a little something like this. And then some key points. I'm just going to go ahead and highlight some key points. So we have 0, 0, top out at pi 2, and then we go bottom back out at 2 pi 0. And then we also have our midpoints as well. So we're going to have 1 pi over 2 right here. Pi over 2, 1. And then we are so, just ignore that for right now, actually. Yeah, just gotta ignore these points for right now, actually. I think I'm misreading my notes. So let's go ahead and just go ahead and plot some of these points that we have right now. All right, so we have a 0, 0, and then we have a pi 2. So let me go ahead and actually go ahead and put this out. So yep, we have a little pi 2 right there. And then we also know at 2 pi we go back. So we don't really have a ton to tell us just yet. Okay, now I remember what I was going to tell you. So right here, if we go ahead and look, we know that at values of like pi over 2 and 3 pi over 2, that we're going to get cosine of pi over 2 and such is going to be 0. So therefore right here we're going to get 3 pi over 2, 1, and then pi over 2, 1 as well, right here. So now we can go ahead and plot those. So we know we go straight up 1 unit. And then we can also see that at 3 pi over 2, we can go straight down 1 unit. But that also doesn't tell us a lot just yet. So let's also try to look at some other interesting points as well. So some easy to work with points for cosine would usually be like pi over 3 and those values, just because we don't have to deal with square roots. So then let's see, at pi over 3, we get 1 minus 1/2, so 1/2. And then at 2 pi over 3, we get 1/2 minus a negative 1/2, so we get 3/2. So now we have a couple more points to put in there. So we get 1/2, go up pi over 3. And then we can go 1.5, and then once again, kind of pi over 3. We'll pretend that looks a little bit better than what it does. All right, So now that gets us a little bit more of something. So now let's see if there's anything else we can use. So if we go ahead and we look at our Cartesian graph, this is actually something that helps us out. So we discussed like way earlier, and like I think even 2413, about how if we had f of negative x equals f of x, then it would be even and have symmetry around the y-axis. And that's pretty similar to what we said over here, to where f of negative theta is equal to f of theta, we're going to be symmetrical around the polar axis. So in this one, it's actually pretty easy to see. If we look at our polar graph, that this is going to have some symmetry between. We can look at this symmetry here and see how we can go up here, and how we know this is going to repeat itself. So we can say that f of negative theta is equal to f of theta. So therefore, we're going to have symmetry over here. So then we can go ahead and connect our points, and we're going to get something that looks a little like this. And this right here is going to be called a cardioid, this shape. And that's because, and it's usually characterized by having this little point right here. And it shapes that because it looks like a heart. Okay, tangent lines. So we said earlier when we were converting that x is equal to r cosine of theta, and y is equal to r sine of theta. But we can also rewrite these as saying that we can go ahead and rewrite these and replace r for f of theta. So we can get f of theta cosine of theta and f of theta sine of theta. All right. And then, so now what we're doing now is we have actually gone and defined x and y as a single third variable. So we've essentially turned this into we've turned this polar into parametric essentially. And last week, when we were trying to figure out how to derive parametrics, we said that dy over dx is going to be dy dt over dx dt. But in this case, we're in theta. So we have dy over d theta over dx over d theta. So then what we can do, if we take the derivatives of those separately, we're going to get, by using product rule, we're going to get dr d theta sine of theta plus r cosine of theta over dr d theta cosine of theta minus r sine of theta. So when we're doing tangent lines, essentially it's kind of the same thing we did last week. It's just this formula is a little complicated. It can get messy to work with. But let's go ahead. But it's just messy, but it's not like super hard usually. So let's go ahead and do an example with this. In this example, we want to find slope of tangent line. Of r is equal to 1 plus 2 cosine of theta at theta is equal to pi over 3. All right, so now that we have that, let's go ahead and look and see what we need in our formula. So we have our r, we have our sine and cosine, that won't change. We do still need our dr d theta though. So if we go ahead and derive our r, dr d theta, 1 goes down to 0, and 2 cosine of theta goes to negative 2 sine of theta. So now at this point, it's mainly just about plugging things in. So usually with this, I find it easier to split this up in between the top and the bottom. Just do those completely separately and then divide, because I feel like sometimes it gets to be too many numbers and a bunch of trig stuff, so I usually find it easier just to go ahead and do them separately. So let's go ahead and just solve for dy d theta first. So whenever we do that, if we go ahead and plug in our dr d theta, we're going to get negative 2 sine of theta times sine of theta plus our r, which is our initial formula, so 1 plus 2 cosine of theta cosine of theta. So when we go ahead, we can plug this in. We can plug everything in, so we get negative 2 sine pi over 3 sine of pi over 3 plus 1 plus 2 cosine of pi over 3 cosine of pi over 3. All right, then we can just go ahead and plug in chug. We're going to get negative 2 square root of 3 over 2 square root of 3 over 2 plus 1 plus 2 times 1/2 times 1/2. We can go ahead and cancel it, break this down a little bit more. This will cancel to where we can get negative 3 over 2. This right here, 2 times 1/2 will go to 1. So then we're going to get 2 times 1/2, which is 1, which is negative 1/2. So now for our dx d theta, we know that that is going to be equal. We go ahead and plug in our dr d theta, so negative 2 sine of theta times our cosine of theta minus our r, so 1 plus 2 cosine of theta times sine of theta. All right, so we can just go ahead and plug in pi over 3. So then we can get, 2 sine pi over 3 cosine pi over 3 minus 1 plus 2 cosine of pi over 3 sine of pi over 3. We're going to get negative 2 square root of 3 over 2 times 1/2 minus, we're going to get 1 plus 2 times 1/2 times square root of 3 over 2. If we go ahead and clean this up a little bit, we can go ahead and cancel out one of these 2's to where we get square root of 3 over 2. And over here we can get, that's going to, 2 times 1/2 will go down to 1. So then we're going to get, minus square root of 3 over 2 minus square root of 3. We can go ahead and combine that to get us yeah, we can go ahead and combine that, and we can get negative 3 square root of 3 over 2. So now we can just do our dy d theta over dx d theta to get us negative 1/2 over negative 3 square root of 3 over 2. These negatives will cancel, these over 2's will cancel, so we get 1 over 3 square root of 3, and we are done. All right, so now let's go ahead and move on to areas and arc lengths and polar. All right, so whenever we go ahead and do this, our main formula that we need to know is that our area is going to be equal to the integral from our A to B, or our two angles, or two thetas, from, and it's going to be of 1/2 r squared d theta, where r squared is, of course, our f of theta. All right. So whenever we go ahead and we, however, it is easy, well, it's easy just to think on paper that we can just go ahead and plug and chug. That's actually not really a great idea. Whenever you work with areas, you really want to get a good look at the graph, because let's say you have a graph like this. Let's say you have some sort of a limit, like let's say you have some sort of limicin where it has kind of like a weird little hole in the middle. That can be kind of weird to solve for. So usually what you want to do is you need to look at the graph and see if you need to go ahead and break it up into smaller chunks, because, like I said, the math when you get to like this little like hole in there is kind of weird. So usually what I would try to do is just solve for each individual piece. So go from like, and essentially like I would split this one up into like 3 pieces. So I would go from like this, like do like this half that doesn't have the hole, the other half that doesn't have that, and then just do like the little like gap in there separately. So it's really important to get a good look at it. And it's also good to try to get a look at the graph, because sometimes it can kind of give you an idea of where your bounds need to be. Sometimes if they don't give you bounds, you can maybe assume it's going to be pi and 2 pi, but once again, you have to double check and think, do I need to break this up? Do I need to go ahead and, do I want to use symmetry? Do I want to go ahead and do I need to make any special modifications whenever I solve this area? So let's go ahead and do an example. In this one, we just want to find the area of r is equal to 3 plus 2 cosine of theta. So the graph for this one is going to look a little something like this. So usually if you're doing this, I would go, if you're doing this on homework, usually what I would do is I would even go into Desmos, and usually on their online like polar calculator, they even give you like the option to set your bounds. So that's another thing you can kind of play with and be like, okay, where is this symmetrical and things like that. If you are doing this on an exam, I would maybe just try to plot some like sample points and just kind of see where they fall on your graph. But this one does not have any like weird little like gaps in it. So what we can do, so this one's pretty straightforward. And for this one, if we want to go ahead and like, let's say we weren't using Desmos and we wanted to see if like we could see where things fell on our graph. I usually just try to pick some sample points at like every multiple of pi over 2. I don't know what just happened there, but okay. All right, so whenever we do this, yeah, we can go and maybe plot some sample points. So let's say at theta equals 0. I kind of drew this a little off, but it's fine. Theta equals 0, we get cosine is going to be equal to 1, so 3 plus 2, this is 5. So yeah, that looks right. Let's say theta is equal to pi over 2, we get 3. And then theta is equal to pi, we get 3 minus 2, so that's going to be a -1. Like I said, I drew this one a little bit off. When I put it into Desmos, like it looked better. Like there we go. And then theta is equal to 3 pi over 2. We go down to -3. And then when theta is equal to 2 pi, we go straight back and we end up right here again. So therefore, this one looks like it'll be from 0 to 2 pi. And this one's pretty simple in that we only have to break we don't have to break this one up. So we can go ahead and know that our bounds are going to be from 0 to 2 pi. Wait, am I not sharing my screen? Yeah. Oh, yep. It X'd out for a second. There we go. All right, there we go. So especially since, let me make sure it's still. All right, it's saying my connection is down. All right, let me see if that, okay, good, that's showing up now. All right. So especially since I know this is going to be recorded, let me just kind of just do a quick little recap of this. Essentially, I think when it went down, I was mentioning that make sure you draw your graph of your function, just so you can kind of get an idea and see if you need to make any modifications or split up the integral in any way. And then because that can usually help you kind of determine what your bounds are. And then after that, I said, I went ahead, I drew out our graph for our equation right here that we're going to do in our practice problem. So then I went ahead and did that, and then I mentioned a good way just to double check your bounds to see like where all you need to go is to plot some sample points. So for example, I plotted theta equals 0, pi over 2, pi, 3 pi over 2, and then 2 pi. So like for example, usually with circles, like you only have to go to pi and you're good. So that's why I went ahead and wanted just to mention that. So, but now that we have our bounds established, we can set up our integral. So we can say that our area is equal to the integral from 0 to 2 pi of 1/2 times 3 plus 2 cosine of theta squared d theta. All right, so I usually to go ahead and pull the 1/2 out in front. And then let's go ahead and FOIL out this little inside, the 3 plus 2 cosine of theta squared. So 3 squared is 9. We're going to get 3 times 2 cosine of theta, so 6 cosine times 2, so 12 cosine of theta. And then 2 cosine of theta squared is 4 cosine squared of theta d theta. All right, so we have this now. It's a little cleaner, but the main issue, though, is that we have that cosine of theta there. And we can't really do anything with that since it's not multiplied times like a sine or anything. So we're going to have to go ahead and use our power reduction in order to actually integrate. So I'm going to go ahead and expand this out a little bit. So we're still going to keep our first two terms the same. But our third term, we have to do 4. And we remember that cosine squared of theta is equal to 1/2 times 1 plus cosine of 2 theta. All right, so now we can go ahead. I'm going to go ahead and kind of simplify that down to 2. So now we can rewrite this to get us our 1/2 right there. We can get 9 plus 12 cosine of theta, plus we have 2 times 1, so 2, plus 2 times 2 cosine of 2 theta d theta. All right, now we can go ahead. I'm going to go ahead and kind of combine this and this to get us plus 11. So now we can go ahead and integrate. So we're going to have 11. If we integrate that, we're going to get 11 theta. $12 cosine of theta. So if we integrate that, we're going to go ahead and get the integral of cosine is going to be sine, so 12 sine of theta. And then if we integrate 2 cosine of 2 theta, so we're going to keep our sine of 2 theta. And if we think about this, and if we went ahead and derived our sine of 2 theta, we would get 2 cosine of 2 theta, so we can go ahead and leave that. And then we're going to go ahead and integrate from 0 to 2 pi. All right, so I'm going to go ahead and, actually I'm going to go ahead and distribute our 1/2. Why not? 11 over 2 theta plus 6 sine of theta plus 1/2 sine of 2 theta from 0 to 2 pi. If we plug in 2 pi, we're going to get 11 halves times 2 pi plus 6 sine of 2 pi plus 1/2 sine of 4 pi. If we plug in our 0, we're going to get 11 halves times 0 plus 6 sine of 0 plus 1/2 sine of 0. All right, if we go ahead and solve these up here, on our top one, we can get this 11 times 2 pi can cancel to just 11 pi. And then we have sine of 2 pi goes to 0, and then sine of 4 pi also goes to 0. So we get 11 pi. And then over here, we're going to get 11 halves times 0 is gone, 6 times sine of 0 is gone, and then sine of 0 is gone. So therefore, our final answer is 11 pi. So since we are running a little short on time, I'm going to go ahead and just kind of show the setup for the next ones, but I'm not going to integrate them. So in this example, we want the area of the region inside r is equal to 4 sine of theta, and outside r is equal to 2. So the first step that I would do here is go ahead and draw our graph. I don't know why well, okay, I'm just going to draw it like this. We're just going to overlay it. It's fine. So we go ahead, let's go and draw our r4 sine of theta in red. So we know it's going to be a circle with the diameter 4 going straight up. And then if we have our r equals 2, we have a circle centered at the origin with the radius of 2. So therefore, the section that we're going to be covering, that we want to find the area, is this section right here. So when we think about this and we have our area formula, it's essentially taking this section right here. We want to go ahead and figure out this section right here. So what we want to do is we want to go ahead and we need to find the area of this bigger one, and then we need to go ahead and subtract the area of this smaller one in order just to get the green. So the first thing we need to do is figure out where our points of intersection are. So the easiest way to do that is go ahead and set the radius equal to each other. So we can go ahead and get r is equal to 4 sine of theta is equal to r equals 2. So 4 sine of theta is equal to 2. Then we're going to get sine of theta is 1/2, which we know happens at pi over 6 and 5 pi over 6. And if we go ahead and we look at our graph, we can see this still makes sense. This does look like it's at pi over 6. This looks like it's at 5 pi over 6. And that's another good reason to keep is that you want to have a picture of the graph, is because sometimes your points of intersection are like kind of weird, especially when you're dealing with like cardioids and limicings. Because sometimes when you try to solve them and set r equal to each other, it's kind of weird and a little wonky. So that's why reason number one why you want to draw your graph, and also just to double check and make sure that your like bounds make sense. So now that we have our bounds, we can go ahead and set this up. So we're going to have our area is equal to 1/2 going from pi over 6 to 5 pi over 6. And we want to take our bigger one, So, which is going to be our 4 sine of theta, and we're going to square that, minus the section that we have from that little piece that we have of our smaller one. So r equals 2 d theta. And that is going to go ahead and be the setup from this point. You can just go ahead and just integrate like you normally would. I believe the answer, assuming I didn't have a math error, should be 2 square root of 3 plus 4 pi over 3 if you want to go ahead and do that on your own time. So let's try another one. In this one, we want the region inside both curves. And our curves that we have are going to be r is equal to 3 sine of theta, and r is equal to 3 cosine of theta. So once again, our first step is going to be to go ahead and draw our graphs. So I'm going to go ahead and draw the first one in red. So we have r is equal to 3 sine of theta, so we know that's going to be a circle going straight up with the radius of 3. I mean diameter of 3, I misspoke. And then r cosine of 3 is going to be a circle going straight out to the right, once again with a radius of 3. So then, since we're trying to find the region inside these two curves, we know it's going to be this section right here. However, sometimes whenever we're dealing with the region inside two curves, once again, things can get like a little wonky, a little messy sometimes. So let's go ahead and actually, I'm going to go ahead and try to draw like a little zoomed in version of this region. All right, so we know that this little, so then actually I'm going to go ahead and then draw like little like extra. All right, so if we look at this, we can actually see that this region is going to be perfectly symmetrical. And this is actually really, really helpful to us in this situation, because whenever we think about taking the region of the graph, it's essentially kind of because whenever we think about taking the area, we're essentially kind of saying, okay, we have like, let's say we're going from 0 to that point of intersection. We are taking this little chunk from here, from like here to here. And this one's actually pretty easy for us, because what we can do now is we can actually only have to worry about this section right here. This little section that's part of that red circle, that was part of our r equals 3 sine of theta. We don't have to worry about this piece anymore, just due to symmetry. So what we can actually do is we can take our point of intersection. So we can once again solve that by setting our r's equal to each other. 3 sine of theta, 3 cosine of theta. Sine of theta is equal to cosine of theta. Tangent of theta is equal to 1. And it looks like we're about in the first quadrant, so therefore we can say pi over 4 is our intersection. So what we can do is we can actually just say, make this easier, and just say that we're going to go ahead and solve for this little, and just solve for that little piece. And just say that we're going to go ahead and just solve for that little piece, because if we say that we're going from 0 to pi over 4, we're just going to solve of 3 sine of theta, this setup right here, then that's just finding that little red piece. And then what we can actually do is we can go ahead and multiply the entire thing times, but since that's just that little section, we have to multiply the whole thing times 2 to get us the full thing. So then therefore our setup is actually going to be, our area is equal from 0 to pi over 4 of 3 sine squared of theta d theta. Hypothetically, you could go ahead and use the other one and use our cosine of theta. However, that one's a little messier. That one's not quite as easy to use, mainly just because like your bound isn't going to actually start at 0 for that one. Because yeah, that one's going to be a little wonkier. So therefore, I would try to look at them and just see which one actually has the easier bounds whenever you're doing this. And if you want to solve this one at home, I believe the answer should be 9 pi over 8 minus 9/4. All right, so now let's try to quickly cover arc length. So arc length of polar. So the formula you need to know for this one is going to be that our length is equal to the integral from a to b, or theta 1 to theta 2, of the square root of r squared plus dr d theta squared d theta. And these ones are usually a little simpler to deal with. I mean, it's helpful to definitely look at the, once again, I would try to look at the graph for these. But for today, for this example, to save some time, we're not going to really worry about that. Once again, I am just going to go ahead and just do the setup for this one. And then if you guys want to solve the actual integral yourselves, you can. But I mean, we've spent weeks and weeks covering integrals. So in this example, we have r is equal to theta squared. And then that is going, and then they are also going to give us bounds from 0 to 2 pi. All right. So for this one, we have our, they gave us our bounds. We're just going to assume that, you know, we don't have to make any modifications for this one. 0 to 2 pi. And then we're going to go ahead and do the square root. So we know that our r squared is going to be, that our r is theta squared, so we have to square that. Theta squared squared. Plus, we need our dr d theta, so we take this, dr d theta. A derivative of theta squared is going to be 2 theta. All right. And then at that point, we can just go ahead and simplify down to 0 to 2 pi square root of theta to the 4th plus 4 theta squared d theta. And I believe, and yeah, these problems are usually just plug and chug. These ones typically don't tend to get like super, super complicated. Areas, those can get kind of tricky, and especially with areas, I would recommend doing like a lot of practice problems on those. I believe the answer for this question, if you want to know, is 8/3 times, I can't read my notes. Okay. Eight thirds and then times pi squared plus 1 to the 3/2 minus 1. All right, so that is all that I have prepared for today. I'm going to go ahead and at least stop recording. And all right, there we go. And good luck on all your assignments and have a good day.